Well, dear friends, we have completed so far ionic model of the bonding. Now see the next model of bonding is covalent bond. You know why I am telling model. See, whatsoever we are here drawing the structure or sketching the structure of any molecule, basically that represents the model of that molecule. And all of you are knowing what is the definition of model, how to define any model. So see, model you have gone through various kinds of model in market. You may find model of television, model of car, or model of anything. So how to define model? Tell, if you want to define model, if you want to create some definition of model. So how it can be defined? Say as per my opinion, model can be defined as model means which is not real. This is the definition. Model means which is not the real, but very close to reality. Very close to reality. So in this way we can define. So whatsoever we are drawing here on the paper, on the board, whatsoever we are sketching the structure of any molecule on the paper or on the board, that is a model of that molecule, means that is not the perfect structure of that molecule, that is not the true structure of that molecule, but very close to truth, very close to reality, right? So in this connection, our second model is covalent model of any molecule, covalent bonding. So see here how this covalent bond is formed. So all of you are knowing covalent bonds are formed by mutual sharing of electrons. Mutual sharing of electrons. This is the very simple definition of a covalent bond. As you have seen in the ionic bonding, what is ionic bond? So ionic bond basically is the electrostatic attraction between two ions. So similarly, what is covalent bond? How a bond is defined? Covalent bond is defined. So covalent bond is basically it is the shared pair of electrons. See, in ionic bond or ionic bonding, ionic bond is the electrostatic attraction. So you cannot say covalent bond are similar to the ionic bond. So covalent bond basically, or a chemical bond, you can say covalent bond is shared pair of electrons. It is defined as the shared pair of electrons. Pair of electrons. Shared pair of electrons is called bond, and the pair of electron which are present, pair of electron is known as bond pair of electron. Bond pair of electron, right? So the covalent bonds are formed by the mutual sharing of electrons, means both the atoms will participate or contribute in the bond formation. What is a covalent bond? So the covalent bond is basically the shared pair of electrons, right? Shared pair of electrons. And what is ionic bond? Ionic bond is the electrostatic attraction between the ions. And this shared pair of electron, this pair of electron is known as bond pair of electron. Okay, bond pair of electron. So, dear students, we have so many theories of covalent bonding, like valence bond theory, which includes hybridization, resonance, and all these things, molecular orbital theory. But before going in the detail of all these theory, Lewis structure should be sketched. So before going into the details of bonding theories, covalent bonding theories, we have to know little bit about the sketching of Lewis structure of any molecule, right? So see, so first point I am taking here, rules for Lewis structure, right? So before VBT, before MOT, before other bonding theories, VSEPR model is a different theory. It is not related to the valence bond theory. So formal charge, resonance, hybridization, molecular orbital theory. Before going into the detail of all these, one must know how to sketch the Lewis structure. How to sketch the Lewis structure, right? So rules for Lewis structure, rules for Lewis structure, Lewis structure. So first point, normally two electron pair up, two electron pair up, to form each bond, right? So normally two electrons pair up, and form the each bond. And you know what is the consequence? This statement is the consequence of Pauli's exclusion principle. So this is the consequence of, this is the consequence of Pauli's exclusion principle. Pauli's exclusion principle. As you know, that in any orbital maximum two electrons can have, any orbital can have two electrons with opposite spin. So this is the basically concept. Two electrons pair up. See, I have taken the words very carefully. Normally two electrons pair, not with the parallel spin. So normally two electrons pair up to form each bond. Means suppose that two atoms are bonded with three bonds. So how to visualize that, I'm telling you one by one. So normally two electrons pair up to form each bond, and you know covalent bonds are of two types. We can state here that covalent bonds are of two types. One is sigma and other is pi. Sigma and pi. I will discuss in detail about this sigma and pi bond, but here you can say the energy of sigma bond, energy or bond energy, you can say bond energy of sigma bond is more than the bond energy of pi bond. So you can say that sigma bonds are stronger than pi. Sigma bond, that is, consequence of this is, that is, sigma bond is stronger than pi bond, right? Okay. Now see, suppose that two atoms A and B sharing electrons like this. So normally two electrons paired up I have shown like this, but as per the Pauli's exclusion principle, how to represent this? You can represent like this: A, B, right? These are the A and B. They are the nucleus of atom A and B, and this pair up to form each bond. Or you can represent this like this: A single bond, B. See, whatsoever I have written here, that is I have shown here in this representation. So this is the model of AB molecule. This is the model of AB molecule. And you know how many bond pair of electrons are there? Bond pair of electrons is equal to 1. How many electrons are involved here? 2 electrons, as it is evident. And you know, this is a single bond. This is called single bond. So this bond is sigma bond. Sigma bond. So what conclusion we can write here? That single bond between two atoms is always sigma. See, so this is always sigma. So this is the representation of this. Suppose that I am taking this molecule this time, this representation between A and B. Now tell me how this can be represented, or you can represent this. There are 4 electrons between A and B, and pair in the pair of 2, and you can write here A double bond B, right? A double bond B. Now this is the model of AB molecule, or wait, I can change this so that you cannot confuse. You should not confuse that this is, suppose that this is XY, different molecule I have taken, X and Y, because I have already taken here AB, right? So this is the model of XY molecule, right? How many bonds between? 2 bonds. Both are sigma? Answer is no. Here 1 sigma and 1 pi. So if there is a double bond between 2 atoms, one bond is always sigma and other is second one is always pi. So it means here in this representation, one can explain that these two bonds appear similar, so both have same energy. But here, since I have already explained you that sigma bond is stronger than pi bond, and bond energy of sigma bond is more than the bond energy of pi bond, so you can say that in this model, it seems like a similar bonds, but actually they are different. One has some other property, means some other parameters, and other second bond is different from first bond. I will explain this in the upcoming lectures, how sigma bond and pi bonds are differs with respect to each other, what the point of difference they have, and how this bond energy can be justified that sigma has more energy than bond energy than pi bond. But you should know that, okay, if double bond is there, so both bonds have not same energy, means both bonds are not but equivalent. So this has to be developed. This skill you have to develop, because in the whole chemistry you will encounter million times every time with the molecules, and all such parameters you have to compare, right? So one sigma bond and one pi bond always, means if there is a double bond between two atoms, so there is one sigma and one pi, this is always true. So one sigma one pi in double bond, always, right? But with this model or with this model or with this model, we cannot differentiate between these two sigma and pi bonds. It appears like a same bond. This is the reason why we require some advanced visualization of molecules and bonding pattern. Otherwise, it is sufficient. Lewis model is sufficient to explain the property of molecule. But since all the properties of, let's see, this bond, double bond, both bonds are not equivalent, how you can explain this? Obviously, you can explain this with the help of orbital consideration and other advanced parameters. Okay. How many bond pairs are there? Number of bond pairs is equal to 2. Number of bond pairs is equal to 2. Okay. Okay, good. One more nomenclature we are using here, that here how many nuclei, two nuclei atom of A and B are bonded by 2 electrons. So this type of bond is called 2C2E bond. 2C2E bond. This is also one of the nomenclature of bonding. Means 2C means 2 centers. 2C means 2 centers. And bonded by 2E. 2E means 2 electrons. 2 electrons. So 2C, 2E means 2 center are bonded by 2 electrons, right? So here what nomenclature you can put for this molecule? Here 4 electrons are bonded by 2 center, means you can write here 2C 4E bond. 2C 4E bond, right? So see, this is the first point. Normally 2 electrons pair up to form each bond. So here 2 bonds are there. So each bond involves two electrons with anti-parallel spin. So this is the model of that. Now one more possibility we can see that D and E. Suppose that three electrons are mutually shared, right? So how to represent this? Another way of representation, D and E. How many bonds? One bond, two bond, three bond. So you can write D and triple bond E, right? Now see, how many bonds are there? Three covalent bonds are there. Three covalent bonds are there. Are all three covalent bonds are equal? Answer is no. Here is one sigma and two pi bonds. One sigma and two pi bonds, right? And this is true always. If there is a triple bond between two atoms, then there must be one sigma and two pi, right? 2 pi. So this is true in triple bond always. In triple bond always. So in triple bond this is always true, right? Number of bond pairs. Number of bond pairs is equal to 3, right? Number of bond pairs is equal to 3, and it is called 2C 6E. Two centers are bonded by 2 to 4 to 6 electrons. 2C6E bond, right? So this you can see that this double bond or triple bond, they are the multiple of this 2C2E, and this is 2C2E. Normally two electrons pair up to each bond, so this is 2C2E. So you can see that bonds are formed in the multiple of this 2C2E, right? That two centers and keep the constant. This two centers you can keep the constant, but electrons, I mean, you can pair up 2, 4, 6 like that, right? So this is the first point. Suppose that now if it is given that structure to you and this structure, and it is asked to you that how many sigma bond and pi bonds are present in this molecule, right? So you, on the basis of this analysis, you can simply say that this is single bond, so always sigma, always sigma. This is single, this is sigma, this is single carbon hydrogen bond, this is sigma, this is sigma. So this is the model of one molecule. That molecule is C2H4. This is the model of that molecule. See here, two bonds are there. So one sigma and one pi. So how many covalent bonds are there here? So you can say 1, 2, 3, 4, 5. 5 sigma bonds are there in this molecule. One pi bond is there. So total 6 covalent bonds are there. 6 covalent bonds. Right? and if you individually compare each bond, then all they corresponds the first point what I have explained here in the Lewis structure, right? How many bond pair are there? So 6 bond pairs are there. 6 bond pairs, bond pair of 6 bond pairs, 6 covalent bonds means 6 bond pair is equal to 6 bond pair, you can write here. 6 bond pair, right? And if it is asked, okay, find the how many electrons are present in the valence shell of carbon. So how many electrons, suppose that the question is asked, how many electrons how many electrons are present in the valence shell of carbon in the given molecule, in the given molecule, right? So see how to count this. uh, one bond means 2 electron. So how many bonds are there around one carbon atom? So the number of covalent bond around one carbon atom number of covalent bonds around one carbon atom is equal to 4. See, 1, 2, 3, 4, and means 4 bond pair, and one bond pair involves what, 2 electrons. So 4 into 2 is equal to 8 electrons. So you can count the number of valence electrons around any atom in the given model in this way. You just count the number of covalent bonds, and each covalent bond represents one electron pair, means 2 electrons. So number of covalent bonds multiplied by 2, you get the number of electrons in the valence shell, right? Okay, so first point, hopefully it is clear to all of you. How to express the how to sketch the Lewis structure and what is the meaning of a covalent bond, right? Now come to the second point. This is also very important, because you should consider all these points, then you you becomes expert of sketching the Lewis structure, right? Second point is, for most atoms, for most atoms there will be a maximum maximum 8 electrons in the valence shell, 8 electrons in the valence shell valence shell. This is called Lewis octet structure. Octet structure or octet rule. Right? So for most atoms there will be a maximum of 8 electrons in the valence shell, right? And it is absolutely necessary, and it is absolutely necessary for lithium to fluorine. The question arises, why? Why this is absolutely necessary for lithium to fluorine elements or atoms from lithium to fluorine? So if you examine carefully from lithium to fluorine, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. What is the valence shell electronic configuration? The core of every atom is helium, and this is 2s1, this is 2s2, 2p0, 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5. Right? Now, tell me here in this from lithium to fluorine, how many valence orbitals you have? Not you. Okay, not you. It means atoms. How many valence orbitals from lithium to fluorine have? So another question, how many valence orbitals from lithium to fluorine have? So the answer is, how many orbitals they have? What is the answer? Basically, the valence shell electronic configuration here is ns1 r2 and np0 to 6, right? Or you can say 2s, not n, because I have fixed the lithium to fluorine. So this is 2s2. This is the valence shell electronic configuration. Here 2p0, right? So how many orbitals they have? S subshell, how many orbital? One orbital, and P subshell, three orbital. So the total orbitals is equal to 4. And you know, one orbital can have how many electrons? 2 electrons. So if from lithium to fluorine they have only 4 available orbitals, maximum 4 orbitals. So how many electrons they can accommodate? 8 electrons maximum, because one orbital cannot have more than 2 electrons. So the maximum number of electrons they can have is equal to what? 8 from lithium to fluorine. Right? So and you should always keep in mind that this is also a very important point I am going to write here, that the sum of, for this I am writing the sum of shared pair of shared pair electrons, or you can say bonds into two, you can say bonds into two, and lone pair of electrons, lone pair of electrons is equal to sum of this plus this, or in mathematical form you can write shared pair electrons plus lone pair of electrons is equal to number of orbitals and this is equal to 4, right? Number of orbitals 4. So 4 orbitals can have total 8 electrons. So shared pair of electrons plus lone pair of electrons is equal to what, 4. So to avoid the confusion, I should write here bond pair of electrons, bond pair, right? So bond pair plus lone pair is equal to the number of orbitals is equal to 4, and this is always true for this second period elements, or the elements from lithium to fluorine. Always true. Always true. But remember, this is the maximum. Less than this, they can. Right? Less than this, they can. This is the maximum number of, electrons, 8. But less than that, they can. So this is the maximum number of. So this is important point. Maximum 8 electrons they can have in the valence shell. But less than 8 electrons some atoms may have. Right? For example, if you and one more thing. So this is for the most atoms there will be a maximum 8 electrons in the valence shell, right? And it is absolutely necessary. Discussing about this. Absolutely necessary for lithium to fluorine. So now it is clear, right? And one more thing is here. And here I have clearly cleared this point that maximum 8 electrons they can have, but less than 8 electrons some atoms may have, right? Okay, now one more point I would like to add here, that it is quite common as well, that it is quite common, it is quite common it is quite common as well that atoms of other element also, atoms of other elements also utilize only their s and p orbitals, only their s and p orbitals, right? So this is also very common, right? Now see, suppose that we have CCl4 molecule, CCl4. So what is the electronic configuration of carbon? 1s2, 2s2, 2p2. So the valence shell electrons, how many? 4. And Cl, 1s2, 2s2, 2p6, 3s2, 3p5. Right? So how many valence electrons are there? 7 electrons. 7 electrons in the valence shell, and here 4 electrons in the valence shell. Right? So carbon and chlorine, they can share with 1 electron from each other. So this could be the structure of right, and now see, if you I'm carefully examine this structure. So carbon belongs to the second period, and chlorine belongs to the third period. In the third period, they can accommodate more than 8 electrons because due to the availability of orbital. But here in this molecule, chlorine also have 8 electrons in the valence shell. If you count, then you will find where I have written this formula, shared pair of electrons. So for chlorine, if I am considering this chlorine or anyone, all are symmetrical. So if you examine for chlorine, so you will find that see here, a shared pair of electron, bond pair of electrons. So bond pair of electrons, bond pair, how many bond pair? This one bond pair plus how many lone pair? 1, 2, 3. These are not involved in the bonding, right? So they are non-bonding electrons. So 3 bond pairs. So 3 lone pairs. Sorry, 3 lone pairs. So 3 lone pair plus 1 bond pair is equal to 4, and 4 orbitals, and this is equal to maximum 8 electrons. So here chlorine also accommodates 8 electrons in the valence shell, and carbon obviously have 4 electrons and it shares with 4, so total 4, 4, 8. So for carbon, if you see for carbon, how many bond pair? One bond pair, two, three, four. Four bond pair, four bond pair. So definitely it has zero lone pair. This is equal to four orbitals. So carbon also utilize its four orbitals, and chlorine also utilizes only four orbitals, right? Chlorine will not utilize other orbitals. So in this way you can say that okay, chlorine also obeying octet rule, and carbon also obeying octet rule. See, for carbon it is mandatory, but for chlorine it is not mandatory. It is not mandatory, but for carbon it is mandatory. Similarly, now see another example. If you see, BeH2. So in BeH2, what is the electronic configuration of beryllium? 1s2, 2s2. So in the valence shell, 2 electrons, right? 2p is unoccupied. Hydrogen 1s1, only one electron. So its Lewis structure is like this: BeH and 2 electrons here. Now see, okay, one more point. This you can also represent like this: Cl4 bonds you can put here, and now you can visualize the things, right? See, this you can write or BeH, right? Now see, how many beryllium, how many electrons in the valence shell of beryllium? How many bond pair? 2 bond pair. How many lone pair? No lone pair, because only 2 electrons are there in the valence shell. 0 lone pair. So 2 bond pair is equal to 4 electrons. So maximum beryllium can hold maximum 8 electrons, but here only 4 electrons are there, means only 2 orbitals are occupied. Only 2 orbitals are occupied, right? So there are 4 electrons in the valence shell here. So you can say this is an electron deficient molecule. This is electron deficient. Electron deficient molecule. So see here in this point I have maximum 8 electrons they can have in the valence shell, but less than 8 electrons some atoms may have. So see here, this beryllium may have less than 8 electrons in the valence shell, right? And hydrogen also, hydrogen has 2 electrons, and hydrogen cannot have more than 2 electrons because it has no orbital. No 2s, 2p, only one s orbital is there. So this is the maximum capacity of hydrogen, it is saturated. So you can say hydrogen is electronically saturated. Electronically saturated. Because it cannot have more than 2 electrons in the valence shell. No orbitals are there. So what difference you are finding that if you have gone through in class 10th this chemical bonding, and now you are studying here chemical bonding. See here, I am slowly shifting you on the orbital concept. From the shell concept, I am slowly shifting you on the orbital concept, and I am trying to explain each and everything in terms of orbital, right? So now I'm writing here some more structures, and all of you should think and write all these things. Suppose that BCl, I'm writing directly here, and this is homework for you people, that number of sigma bonds, number of pi bonds, number of bond, number of electrons in the valence shell of boron, right? And number of lone pairs, right? So all of you should, write yourself some more structures. Right? And Li, LiCS3. So this is BCl3, this is H2O, this is PH3, and this is LiCS3, CS3Li, right? So it is better to write CS3Li, not LiCS3, right? So all of you should write all these feature for these molecules. This is homework for you people. Valence shell of boron here in oxygen, in phosphorus, right? Okay, now come to the third point of this. For elements which, for elements with available d orbitals, with available d orbitals, the valence shell can, can be expanded expanded beyond an octet, right? See the availability of, if you see the third period of the periodic table, third period of the periodic table. So third period starts from sodium. So sodium 1s2, 2s2, 2p6, 3s1, 3p0, 3d0. So now see, this is the third cell, starts from sodium. So if you examine, then 5, 3, 8, 8, 1, 9. Total 9 valence orbitals are there. Valence orbital. So 9 valence orbitals means is equal to 9 into 2 is equal to 18. 18 electrons can hold. So third period valence shell can hold. See, is there any example for that? That is a different issue. We may or may not have compounds having 18 electrons in the valence shell, but this is the maximum capacity. This is the maximum capacity. Maximum capacity, right? Means the molecule have or not, that is a different issue, but availability, as for the availability point of view, say they can have maximum 18 electrons in the valence shell, and this will extend from sodium to sodium to chlorine, from sodium to chlorine, right? From sodium to chlorine, this can be expanded, right? Okay, so if you see group 15, group and maximum, I mean covalency, maximum covalency. So group 15, the maximum covalency is 5. Other covalencies, are here 3. Group 16, if you take, then the maximum covalency is 6, and other covalencies are 2 and 4. And if you take group 17, so the maximum covalency is 7, and other covalencies are 1, 3 and 5. 1, 3 and 5. And if you take 18, so the maximum covalency is 8 noble gases, and other covalencies 2, 4, 6, particularly xenon, right? You know, xenon have compounds like XeF2, XeF4, and XeF6 and XeO3, right? So here covalency is 2, here 4, here 6, and here 8, right? See, covalency and number of atoms connected to that atom, central atom, both are different terms. That is called coordination number. So don't see that, okay, here covalency is 2, so 2 atoms, covalency is 4, 4 atom, covalency is 6, 6 atom. So if covalency is 8, so there should be 8 atoms, not like that. I will differentiate between them. This covalency and coordination number, both are different terms. In some cases it may be same, but in some cases it may be the different. So see, group 15, it has maximum 5 covalency, and this 5 covalency you cannot achieve without the participation of this d orbital 3d, right? So in this period, third period, you have d orbitals, because the d orbital starts from third period. So this is possible that you can expand the octet, means beyond third period elements may have more than 8 electrons in the valence shell, right? So we will work out on this, how to justify this maximum covalency and other covalencies in this, actually on the basis of electronic configuration and understanding of orbitals. You can very easily explain this. I will definitely will show you how these valencies, covalencies are satisfied for this these groups and elements, right?